So right-hand rule number 3, this is our last one. So here we have a little diagram that I'd like you to copy into your notes. All right, so right-hand rule number 3, this is the last one, deals with a current-carrying wire that is passing through a permanent magnetic field. Now in class the other day, I did the demo, and I'll record it again tomorrow, where I took this horseshoe magnet with the permanent, that's our permanent magnetic field, horseshoe magnet there, north and south pole on there, and we passed a wire going through it, and when I turned on the current, the wire either moved out or it moved in. So that's what's going on with this one here. Now, very important is that the wire must run perpendicular to the magnetic field. If it's running parallel to it, it won't work. And that's a trick question that often appears on tests and exams. You'll have a wire running parallel to the field, and it'll say, which way does it go? And one of the answers is, it would not be affected by this field. So, because the way the two fields are orientated towards each other, in order for there to be a force, they have to run perpendicular to each other. Natasha? All right, so I've drawn the diagram up on the board here, just so you can see how the right-hand rule works. So with right-hand rule number 3, there's no finger curling, so nothing has to curl around or wrap around. So the first part is your fingers on your right hand represent the field lines of the permanent magnet. Now in this case, this is our north pole, this is our south pole. Field lines are always drawn going from north to south, or how a north pole magnet will react. So field lines are going to point this way. So however you want. What do you think your thumb's going to represent? The direction of the current in the wire. So in this case, it's going down. Now the third component, there's 3 things with right-hand rule 3. You've got the direction of the current flow in the wire, you've got the direction of the field lines of the permanent magnet, and then you have the force. Now in this case, the force is going to be going into the page. And the way that is signified by the palm of your hand. So if you want to think force, just think about if you were to slap someone. You're going to have force coming from your hand, right? And of course, everyone now turns to each other and starts giving high fives and slapping. But that's how we do it. Now, if in this one we reversed the current flow, Julia, what's going to happen? My finger's going to change? These poles stay the same. So my fingers are still going to be pointing this way. Yeah, and then if that would cause the force to come out of the board. Excellent. All right. Did you have a question, Aaron? Sure. All right, so a bit of notation to make our lives easier. When we're dealing with right-hand rule 3 and a little bit with right-hand rule 2, we're dealing with 3-dimensional spaces or 3-dimensional drawings. When you're transferring those to a 2-dimensional paper, it can be a little bit confusing. So we have a little bit of notation to help us out to make this just go a little bit easier. So for the 2-dimensional, the field lines going left, right, up, down, diagonally, it's still the same deal. They look like regular lines. If we want to signify something going into the page, you use X's. And if you want to signify something going out of the page, you use dots. And the easy way to remember that is to think of a bow and arrow. If I were to take a bow and arrow and I were to shoot it towards the class, then you girls would see the tip of the arrow coming towards you. You wouldn't see, so it would look like a circle. Yeah. If I were to shoot a bow and arrow away from the class, you'd see the end of the arrow, so you'd see the feathers, and it would look like an X. All right. One other thing with these dots, don't draw them as dots like that, okay? Actually make them just significant dots.
Show the strength of field.
Yeah, if you're trying to show a field or force, you do it like that. No, because circles would imply something else. They're dots. So using this, using the fact that we have a force being applied, we can actually calculate the magnetic field strength, which is something we weren't able to do before. So Biffle. Biffle. Which stands for these things. It's important to note that for L, or length of wire, if we had a length of wire that went the length of this classroom, but it only passed through this little horseshoe magnet, it's only the length of the wire that's in the magnetic field. So it doesn't matter how long the whole wire is, it's how much of it is in the actual magnetic field. So make sure that you note that. So to sum up right-hand rule number 3, we've got all of this.
Whoa.
I'm recording that. All right. So page 504, questions 9 to 12. And we're going to have a practical and written quizzes in upcoming classes on right-hand rules number 1, 2, and 3. And we're going to talk about that right now and schedule it.
Okay.